his talk as well, probably none. But really interesting stuff, and thank you so much, Ronen, for coming to the school. And
my pleasure.
Keep it a bit interactive. Ask questions.
Okay. So, how long this tutorial takes depends on you. Don't worry, it's not going to take all the time. But I really encourage you to ask questions. I'm going to cover, besides the first part, which is going to be, let's say, the fundamentals, I'm going to cover different topics that are related to multi-agent planning with the classical flavor. So we're not going to talk about stochastic action and things like that. We'll start, most of the tutorial will just talk about deterministic actions, full certainty. But the point is not to cover all of the material, but that you get something out of it. So please feel free to ask questions, clarifications during the middle. I'll be happy to answer and clarify things. Okay. So why are we interested in multi-agent planning? You've all heard of the Internet of Things. You have all of these devices connected to the Internet, perhaps in your house, perhaps across different sites, and each of them can do something useful, but I'm sure they can do more useful things if they are integrated in some way and can coordinate their action together. Robotics is also getting a lot of attention and seems to be coming of age, and if we will have robots servicing us in various ways, helping us in various chores, in various missions, and a group of them somehow meet to coordinate on a task like a rescue mission, then they need to be able to jointly plan, or we need to plan for them. But even if we don't go to this high-tech world, we think about other entities like companies and contractors who can benefit from working together, can maybe produce something together that they cannot produce on their own. Then planning can be useful for them to generate the right process. And finally, multi-agent planning is also a very useful abstraction for factored and distributed planning. I'll talk a lot about this. But the idea is that an agent doesn't have to be a clear physical entity. It could be our own invention, our own abstraction of some component of a system. And in some cases, when we use this abstraction, we get faster solution to single agent problems. So this is a plan of the tutorial. I'll start by going through the space of possible models. I'll probably leave out some of them. I'm not planning to be exhaustive, but you'll see that there's a lot of different aspects to multi-agent systems that you should take into account when you try to model a system. Then I'm going to talk about the multi-agent strips model, the language, and we're going to look at how it's used to do factor planning, and two fundamental algorithms. One is constraint-based planning, or you can also describe it as global planning followed by local planning, and the other is distributed forward search. So basically, this is the basic part of the tutorial. And then I'll move on to talk about the issue of privacy. We have a group of agents, and we want to encourage them to collaborate. Sometimes they'll be more willing to do so if they can maintain the privacy of some of their information. So, if a number of companies are trying to collaborate on a joint project, and of course they're going to have to expose some information for this collaboration to work, but they probably don't want to expose too much information. No one needs to know their precise inventory levels or the internal processes that they use in order to produce some of the goods that they have to produce in order to do this joint venture. Then we'll talk about self-interested agents. Agents that basically act only if it's in their self-interest, if it's profitable to them. And then I'll talk about uncertainty. You've had a tutorial about uncertainty, but beyond all the regular aspects, all the standard aspects of uncertainties that you come across when you solve planning under uncertainty, if you move to a multi-agent system, there is additional element of uncertainty that has to do with the need of the different agents to coordinate their actions. And that raises new issues. So, I just want to be clear that there's a lot that is not covered here. Most prominently, if you're interested in, especially in stochastic planning, decentralized quantities, that's a big area of research with a lot of, many articles, a lot of work, deserves a tutorial on its own. Task distribution, that's a problem that was investigated for a long time in the area of multi-agent systems. What happens when we have a number of agents that can perform similar actions, and we have a task that we want to perform, and we need to distribute the work between them in some efficient way. So the issue there is not what actions to perform, but who should do what, how to distribute the load. And so each of these is a big area on its own, and there is a strong bias to work I've been involved with, but I think you're going to see fundamental issues. Okay, so let's start with the first thing. This is more of a high-level look at the spectrum of multi-agent planning problems that we could face. And you can see that there are many different aspects that we need to many different questions that we need to address in order to identify the model that we really need to use. So first of all, who are the agents? Are the agents real agents or abstract agents, virtual? Are they basically our invention, or do they really exist in the world? What is the objective? Are we trying to solve basically to find the most efficient plan, or do we have additional objectives maybe that have to do with the multi-agent nature, such as make sure that the work is distributed in a fair way among the agents, or even more involved notions? Is there a common goal that everyone is trying to achieve, or are there different personal goals that, because the agents are collaborating, can be more easily achieved by sharing some of the work? You know, I do this part for you, you did this part for me. You know, I help you with chemistry because I'm really good in that subject. You help me with physics because you're really good in that subject. Although we could, you know, each do it on our own. And so that's another thing. Is privacy an issue? So does the agent care about the privacy of their information? And do they share capabilities? In which case, task distribution, the idea of how do we distribute the work is important. Can they act simultaneously? So in some cases, when agents act simultaneously, their actions interact. You know, we know how to describe an action of a single agent, but what happens if I perform an action that, you know, we know how to describe, you perform another action that we also know how to describe, and we do it at the same time. The result may not be the aggregation of the results of the two actions separately. Who is doing the planning? Do we have a centralized entity that is planning for the system, or are the agents that are going to take the actions planning for themselves? And all the orthogonal issues that are not specific to multi-agent systems, you can also, of course, you can also make the models more complex by talking about uncertainty, temporal issues, resources, oversubscription, and so forth. So, let's just look at these issues in a little more detail. So who are the agents? So we can have real entities like people or devices or companies. We can have virtual entities like software agents. And we can have abstract agents. So some component of a system. And we are free to decide. It's our abstraction, so we are free to decide what is this component. And I'll give you an example. but I don't know if, I think that Patrick told me that in the tutorial he talked a little bit about logistics planning. So in logistics planning, we have to move around packages between different locations. We have trucks and airplanes, and this is usually a single agent, this is considered a single agent planning problem because, well, first of all, it always appears in a single agent domain, but you know, there's a shipping company, it's in charge of this issue, and it's the one that wants to solve the problem. But you can also think about it as a multi-agent planning problem, where the agents are the trucks and the planes, and it's a useful abstraction in some cases to consider these elements as agents that somehow need to work together to solve the problem. We'll see more about this later. Are there common goals? So agents may have a common goal like building a house, delivering packages, or they may have their personal goals. So as I gave you the example of studying for the exam, but you know, two shipping companies, maybe one is stronger in the UK, has a larger fleet, and the other is stronger in mainland Europe. And so it's beneficial for them to help each other out. You know, I deliver packages for you in the UK, you deliver packages for me in France. It's cheaper for both of us if we collaborate this way. And of course, we can have both of these things. And what is the objective? Okay, the objective we usually think about if we come from the single agent planning perspective is cost optimality. And that's basically the efficiency of the entire system. If you think of cost optimal plan, it's the minimum cost of the entire plan. So it's looking at the efficiency of the entire system together. And that makes a lot of sense for a system that has a single owner. So in the logistics example I mentioned, you know, the logistics company cares about the total cost of moving the packages around, not about the cost per truck. And there's some cases where agents, you know, have to collaborate because of some agreement between their, let's say, parent companies or robots that were sent out for things like that. And that's another case here. Another example I mentioned is the Internet of Things. You know, if you have a lot of devices in your house that are all connected to the Internet and you want to maybe achieve a goal like cooking breakfast, then of course you don't care too much about the workload of the microwave versus the workload of the kettle, right? So that makes sense in these settings. But in some cases, what you care about is some fair division of the load. So maybe if we're sending, different countries sending our robots to a certain disaster area to solve, help do some rescue and mission, then we also want to make sure that there's no single robot that does too much work. Okay? In that case, what we can look at is the minimizing the maximum load per agent. So we want to make the agent, the load on the agent that works the hardest during the plan, as low as possible. That will usually make the load a little more equal among the agents. But that's just one notion. There's a lot of work on this issue of fairness. There's this whole area called social choice theory, and they work about defining and finding algorithms for solving this fairness issue, defining the right notion, and so forth. Another option that we have is selfish agents. So what's a selfish agent? It's an agent that will participate in the plan only if it's in its own best interest. And what does it mean in its own best interest? We usually think of it as maximizing its utility. And so we try to, a natural thing in planning is to maximize the value of the goals achieved minus the cost of its own actions. This is a natural way of defining the utility, but you can define it differently. So the general idea is to maximize expected utility. There's no global objective. For a plan to work, we have to make sure that each of the agents that is participating in the plan is motivated to do so. It's not like the robots that we send to the rescue mission, they do what we tell them. But in this case, these are independent agents. They will collaborate if it's in their interest. So if you think about contractors in the market that are able to build house, you know, plumber, electrician, roofing specialists, and so forth, they need to combine their skills together in order to build a house. None of them can do it on its own. So they have an interest in collaborating, but we have to, and in order to make sure that, you know, but none of them will agree to collaborate if the profits they get or the money they're paying is lower than the cost of the action that they perform. So in order to solve these problems, it's not enough to think about planning. So planning is just one component of the things you have to look at when you solve these problems. You need to combine ideas from planning and from game theory in order to make sure that not only is a plan executable, which is what we care about in regular single-agent planning, but also that you've taken care of all the issues that have to do with the incentives to the agent or desire to actually take part in the plan. For instance, if you think about all these contractors, they could team up in very different ways. You know, suppose we are all contractors, you know, I can choose a group of you to work with together, but I could also work with a different group. And if we work together, we want to make sure that the coalition we formed in order to say to build a house is a stable one, because perhaps, you know, one of the agents will suddenly get a more attractive offer and will say, no, this coalition is not for me, I need to move to a different one, they will pay me better. So, you have to take into account all of these things. You cannot assume that the agents will actually do things that they're supposed to do. They can lie, you know, the agent can misrepresent the cost of its action in order to gain an advantage. So maybe the idea that I get the cost of my action plus some percent of the profit. So if I lie about the cost of my action, I say that they cost more, then I'm going to get more of the profit, right? How do we make sure that the solutions are executable and useful and appropriate? Okay. Another issue, so this was about the different objectives. Another issue is privacy. In many cases, agents will be reluctant to collaborate if they have to expose their entire domain model. So for example, companies collaborating on a project, or if you think of different, even if you know the culture in many companies, even different departments within a company will often collaborate with other departments but want to keep some of the information private. So we need to come up with algorithms that somehow ensure that this privacy is preserved. We also have to define what it means for the privacy to be preserved. So we need formal tools, we need algorithms for that, and that's a big area of research in the past few years, especially in the multi-agent planning community. And I mentioned the issues of capabilities, so we can have agents that have different capabilities, that's one option. And the other one is agents that have similar capabilities, like multiple trucks in a shipping company, multiple similar robots. And then we have the issue of task allocation, how to best allocate the subtasks to different agents, and what is an appropriate division of labor. Again, this comes back to this issue of what are we trying to optimize. So do we want to make sure that the load is fair somehow, and so forth. Okay, another interesting issue is, can actions interact? So first of all, for actions to interact, they have to occur simultaneously. So if we allow simultaneous actions, then we have to ask ourselves, can the actions interact in negative or positive ways? So a simple example, a box may be too heavy to be pushed by a single agent, and only if two agents push the box, it will move. So that's a case where we have a positive interaction when two agents are pushing the box. Or perhaps a bridge is too sensitive for two trucks to cross it at the same time. So we should only allow a single truck at a time. And that's a potential negative interaction. Or two agents, if one agent lifts a table, you know, if I could lift this table on my own, on the side, my laptop will fall and everything on top of it. Whereas if another person will be here helping me raise it at the same time, then everything will remain on the top and we can move the table. And these issues arise when we look at simultaneous actions. And one of the key problems with simultaneous action is how to represent it. You may get a sense already that, if beyond describing what my action can do, I also have to take into account the interaction between the actions of different agents, then that causes a potential exponential explosion in the number of scenarios I have to take into account, right? Exponentially in the number of acting agents. So that's a key issue. How do we represent interacting actions? Finally, who is planning? Single agent is planning for the system. If there's a single agent planning for the system, that often also raises privacy issues. Do we trust this agent? Are we all as willing to send the entire model to this agent? If it's a distributed team of agents, then we may get some benefit from the hardware, and it could also help us with the privacy issue. And as I noted, all the other dimensions that you could think of in single agent planning, of course, remain relevant in multi-agent planning, but I'm not going to discuss it. Okay, so my point here is that the space of models that you need to think about is very large, and if you are coming up with an algorithm or trying to model a certain problem, it's important that you understand the different aspects of the problem you're looking at and be clear about what it is that you're trying to solve. Okay, so I'm going to, of course, not going to cover all of these dimensions. I'm going to look at the most basic model I'm familiar with, which is the multi-agent scripts model. So you all know what scripts is, I assume. So what is multi-agent scripts? It's a simple multi-agent extension of scripts. For the time being, no interacting actions, but you can add them, and I'll briefly talk about that. I'm going to assume that all the agents are cooperative, so we're not going to, at the first part, we're not going to talk about these selfish agents that may manipulate the system in order to gain advantage. We have this situation like the shipping company where the agents are the trucks and the planes, or Internet of Things where the devices in my own home are the different agents, and they all are working for a common cause. But this can also be relaxed. So this is basically multi-agent scripts is a starting point. You can extend it very much like you do in the single agent case. You have a simple version of PDDL, and you can gradually extend them. Same thing for multi-agent scripts. So what is it? It's a very, very small extension of scripts. The only change is that an action is associated with an agent. That's it. So it's the same as before, but actions are associated with agents. So formally, if this is a scripts problem, you have a set of variables, a set of actions, an initial state, and a goal condition. In multi-agent scripts, instead of a single set of actions, you have a number of sets of actions, each one corresponding to the actions of a different agent. So here we have m agents, m sets of actions. That's it. So, I'm going to use logistics planning as an example. So, let's look at it. So it's a classical single agent domain, but it has natural components that can be thought of as agents. So we're going to model each truck and each plane as an agent. And what are the actions? So if this is what we do, what we have to say, what are the actions of each of the agents? So for the truck, it has its action of loading into the truck, unloading from the truck, and moving the truck. So if we have, say, a London truck, so all the action of loading a package into the London truck in the location that it can reach, all the action of unloading from the London truck, and all the actions of moving the London truck. These are the actions of the London truck. And similarly, for the plane, it's the same thing, load, unload, and fly. So if we have a plane maybe that flies from Israel to the UK, then it can, the fly action are its own action, and loading and unloading from the plane would be the actions of the plane. Okay? So notice that the actions move and fly, they only involve the respective agents that the action belongs to. So moving a truck just involves, okay, I have to be clear on this. This action is an action that basically doesn't affect the state of any other agent, or anything more, even more than that. It doesn't affect anything that could impact any other agent, because it only changes the location of the truck itself. It doesn't impact any other object. Similarly for fly, which only changes the location of the airplane. It doesn't impact any other object. Whereas if you look at the load action, when you load a package into the London truck, it impacts not only the London truck, which has a package in it now, it also impacts the package. Now the package is not an agent, but it's an object that is accessible to other agents. So when we load the package into the London truck, then we're indirectly affecting the abilities of other agents to do something. Say if we load the package into the London truck at Heathrow Airport, then the plane cannot load the package, right? And this leads to a very natural notion of global and local variables. So it's a derived notion. It's not, you start with a multi-agent strips model, and this idea is implied, is derived from the model. You don't have to define it as something external. So a variable V is local to agent I if it does not appear in the description of any action of any other agent. So the location of the London truck, okay, what is the only action that impacts the location of the London truck are the move actions of the London truck, right? It doesn't appear, the location of the London truck doesn't appear in the description of the load action for other agents, okay, only for the London truck. It doesn't appear in the unload description of other agents, so it only appears in the description of actions by the London truck. So we call this a local variable. Okay, this is a variable that's local to the London truck. Any variable that is not local is global. What does it mean to be global? It means that this variable, or this primitive proposition, is basically appears in the description of actions of more than one agent. So for instance, the package being at the Tel Aviv airport, okay, that can appear in the load and unload action of the international airplane, because we can load and unload a package in the airport. And it also appears in the description of the truck in Israel, okay, that can load and unload the package in the Tel Aviv airport. Okay? Is this notion clear? Again, please don't be shy, ask questions. My goal is for you to understand as much as possible, and not to cover as much as possible. Okay. We don't only have local and global variables, we also have local and global actions. Again, this is a derived notion. An action AI that belongs to agent AI is local to that agent if its description contains only variables local to this agent. So the move action, if you move, what are the preconditions of the move? Being at the truck being at the origin. What are the effects? The truck being at the destination. Okay? So the only things that appear in the description of the move action are the location of the truck, in the precondition and the effect. The location of the truck, we agreed, or we saw before, is local to the truck. So this action, which only impacts and is only impacted by local variables, local propositions, is called a local action. Okay, so local action does not affect, nor are they affected by actions of other agents. There's nothing that other agents can do to impact the preconditions or the effects of this action. And all other actions we'll call global. So loading the package to the London truck at Heathrow is a global action of the London truck. Why is it a global action of the London truck? Because a precondition of loading the package is that the package is in Heathrow, and an effect is that the package is no longer at Heathrow. And the package being at Heathrow is a global proposition, because it appears in the description of multiple agents. So this is a global action. Okay? So here's another example illustrating this. So in this domain, this is a logistics domain, we have 4 different trucks. Okay? We have 2 packages here. And the trucks, each of the trucks can travel on, can reach locations that correspond to its own color, as well as these hubs or places where they can exchange goods. So this green truck can be in green 1 and 2 and in A. The red truck can be in 3, 2, 1, red 1, 2, 3, red, and A and B. The blue truck here can be in 1, 2, B, and D. And this, I guess this is purple. The purple truck here can be in yellow 1 and in D. Okay? Okay, so the package being in green 1, so this is different to the example that I've mentioned in the previous slide. Look at it, the package being in green 1 is what? It's local. Well, it says so here. It's local to this agent. Why? Because the only agent that has an action of either loading or unloading the package here is this green truck, because all the other agents can't really reach this position. Okay? So only agent T1 is affected or affects this fact, so it's a local fact. And the location of the second of the location of the truck T2 being at red 2 is also a local fact, because only truck 2 is affected or can affect its location, okay? And therefore this is a local fact. The package P2 being at B is a global fact. Why is that? Because both the blue truck and the red truck can reach location B, and both of them can either load or unload the package at this location, and their load and unload action have the location of the package as either precondition or effect. And so the description, this fact, appears in the description of actions both of T3 and of T2. So this is a global fact. The action of driving truck 1 from A to green 1 is a local action, because it involves only the location of truck T1, which is local to truck T1. So this is a local action. Okay, well, the animation here is not really important to the example, but we have to play it. Okay, the action of unloading package 1 by truck 1 at this location, okay, this action is a global action, because because the location of the package impacts both the action of loading and unloading by truck 2 in A and loading and unloading truck 1 in A. Okay? So this is a, okay. Fine. So unloading the package at A by truck 1 is a global action. Okay, I hope that the notion of local and global propositions or facts and local and global actions is clear. Okay, yes. Oh, good. Question.
Okay, yes. So you mentioned, if you go back to the previous line, nice animations, by the way.
Not mine.
Okay, so once you get the package to the red, so the other guys can do something on package 1, right? So you said that package 1 at green is a local fact.
Yes, and also package 1 at 1 is a local fact to agent T2, because only agent T2 can access location 1, and therefore the proposition at package 1, red red one, okay, is private to that agent because only it can impact it, only it can change its value, more basically, it's the only agent that has this fact in the description of its actions.
But T1 had this description in the effects that he can play.
No, in A. If T1 cannot reach this position, only A.
Also, P1 cannot reach the red. Cannot reach.
No, okay. Yes. Each track can only travel on its own color and adjacent black areas. So the black areas are places where a number of tracks can reach, and the colored places are only places that the colored relevant tracks.
If track 1 could place package 1 on red, now this fact will no longer be local.
Exactly. So yes, if track 1 could drive into this position, then being at this position, okay, let's suppose track 1 could drive here. If track 1 could drive here, then track 1 being at this position is still a local fact because it only impacts track 1. Nothing in the description of any other agent involves the location of track 1. This is why it would still be a local fact. But the package being here will no longer be a local fact because there are two agents that have actions that involve the location of this package. If agent T1 can reach here and agent T2 can reach here, both of them can either load or unload this package in this position, and therefore at package 1, red 1 becomes a global fact. Questions? Yes?
So that you can have a constraint between two local facts in different agents, right? So the position of P1 is a local fact for the green agent when it's on the left-hand side there, right? So at P1 green 1 is local, but at P1 red 1 is also local to another agent, and there's a constraint between those things because they can't be in two places at once, right?
Right, and so some of the work that on okay. So this issue of privacy and local and global has also to. We're going to use it in the algorithm, but it also has to do with. It's also a way for us to capture private things, and this constraint that you mentioned is something that is exploited, whereas these algorithms that work on the issue of privacy try to deduce this constraint in order to provide better information to agents when they compute heuristic functions. But the constraint exists, as you said, but I have nothing to say more about it in the context of the first part, but in the case of the issue of privacy, then people try to deduce constraints like this in order to have better information about the domain and then compute better heuristics. Okay. Okay. So, I hope you got the basic settings. So we have this set of agents. Each one has its own set of actions, and we're interested in solving a planning problem with complete certainty and with a common goal. And now I want to talk about two basic algorithms for solving this problem. The first one is basically a global planning and combined of two phases, a global planning phase and a local planning phase. And it was basically the first type of algorithm that was generated for these problems, and its motivation actually came from the single agent case. I'll explain this soon, because it gives us a way to analyze theoretically the complexity of planning by decomposition. But for many years, this area is not that old, but for quite a few years it was considered not a very good algorithm, because distributed forward search, which is the second algorithm that I mentioned, was the most much faster. But if you actually combine ideas from forward search with these ideas, you now have very strong planning. So there's a planner that will appear in the main conference. There's a paper in the main conference that will describe a method for basically doing this global followed by local planning, where the global planning you use forward search, and that's a very effective method. Distributed forward search is still a very efficient way of doing distributed multi-agent planning, and it also gives us some additional insights into decompositions. Okay. So, again, we're in a fully cooperative system. In fact, originally, this was considered as the agent or abstraction of components of a single agent planning problem, like in the logistics domain, which is a classical single agent domain, but I think you agree that it has natural components that it's not clear whether it's useful to think of them as agent or two or not. I'll show you that in some cases it's useful to think of these components as different agents and think of the problem as one of multi-agent planning rather than single agent planning. Privacy is not going to be an issue for us at this stage. And we're going to start with the assumption that there's a single planning agent, okay? But if there is a single planning agent, then single agent planning is the same as multi-agent planning. What's the difference? Single agent is, gets all the information from all the agents, so it's basically solving the logistics problem. Nothing new here. And the main question is, can we, if we look at it as a multi-agent planning problem, can we get anything from that? Okay? Is there any benefit to that? And the idea goes back to a notion that people in planning have looked at for quite some time, and not only in planning, in generally in problem solving in AI. Right? The idea of decomposing a problem. You have a big problem. It's usually exponentially expensive to solve it. Maybe if you could divide the problem into many smaller problems, each of which you can solve almost independently, you will be able to get an exponentially reduced running time, right? Instead of solving one big problem, say we solve 100 small problems, each one is 100 times smaller, but because the problem is exponential, each one of them is exponentially easier to solve, and we just need to solve a lot of them, but that's not a linear number, not an exponential number of them. So the idea is to transform a single agent system into a multi-agent system, moving from strips to multi-agent strips by partitioning a set of actions. So in multi-agent strips, what's an agent? Basically it's a set of actions, right? So we're going to associate the idea of an agent with a subset of the action. And the main intuition is the agent have little interaction with each other. We might be able to solve multiple small planning problems, combine the solution somehow, and get potential exponential gains. So the key question, how do we decompose a planning problem? So in the logistics domain, it seems natural. Let's make the agents of trucks and the planes. But who said that this is the most efficient way of decomposing a problem? Still, in many domains, you have a natural notion of agent, and that's what people have used traditionally. But you can also try to automate the process. Then we should ask ourselves, if we have alternative decomposition, what makes one decomposition good and better than the other? Can we identify this ahead of time? And how can an algorithm exploit this decomposition? And will it bias anything computationally? And just a small disclaimer, this is just one approach for problem decomposition. Makes a lot of sense in the context of planning, but it's just one approach. So, but it's the origin of some of the work in the classical planning community on multi-agent planning. So, we want to understand if we can do something with this decomposition. So let's look at different scenarios we can think of. So, okay. One case is a fully decoupled problem. So we have agents that have no influence on each other. That means that each agent requires and affects different primitive propositions. That means that all the variables in Notion that we've used so far are local variables. In that case, each agent can plan separately, right? for its own the subgoal that it can achieve. It's the only, since all the propositions are private, then each subgoal can be achieved only by a single agent. Each agent will plan to that subgoal, and that's it, we're done. So we get many smaller single agent planning problems. Each one solves it. And there's really nothing to combine them, because they're independent. We can combine the actions however we want. They don't influence each other. So we get exponential decreasing complexity. So imagine you have the logistics domain with two companies doing the package shipping, FedEx and UPS. And when you send a package, you send it either via FedEx or via UPS, and they all use their own fleets of trucks, fleets of planes. So really, these are two independent planning problems. There's no use making life harder for a planner by making it solve this combined problem. It solves the UPS problem, the FedEx problem, and the solution is a combination of both. Okay, not so natural, not so interesting, right? We don't have many examples of this. The other extreme is a fully coupled system. Okay, every agent action impacts every other agent. It impacts the ability of all other agents to use their actions. So all the variables, all the propositions are global and are used by everyone. And it seems that our abstraction of thinking of different sets of actions as agents is not going to bias anything. Okay? I have to be careful here. I don't know how to do anything in this case. Maybe one of you will find a way to exploit the situation as well. But right now, it looks like a situation where this abstraction of the system as a multiple components is not going to bias anything. What's the interesting case? The loosely coupled systems. So there are some interactions. Most agent actions affect only few other actions. In fact, most agent actions affect only themselves. So if you have different shipping agents that serve different areas, like in the example that I gave you, right? They only have these places where they interface, but most of the actions are done in their own area. They don't impact anyone else. That's a good example of this. So there are going to be many local actions and many local variables. In fact, if you think of it, when you think about planning, why is planning successful? Planning is successful because we assume that most actions influence only a small number of variables, right? If every action influenced all the variables in the world, then most of our techniques for generating heuristics and so forth would be we probably have to expand the whole state space, or a very large portion. Same thing here, The interesting case is where there is interaction, but it's limited in some way. So this seems like a natural setting to study, and we're going to look at how we could exploit the situation. Okay. So here's a simple algorithm that exploits decomposition. Remove all the local actions and all the local variables from your problem. Okay? By this I mean, first of all, removing the local action. That's simple. Removing the local variables. If you have a local precondition to an action, remove it. If you have a local effect, remove it. Just stay with the global actions, and with the global action only caring about the global proposition. Solve the resulting problem. This is usually going to be under our assumption that most of the actions are local and most of the variables are local. You're going to get a very much smaller planning problem. Solve this planning problem, and what do you get? This basically gives you a skeleton of the global skeleton of your solution plan. And the global actions are the actions that require coordination, that coordinate between different actions. They affect multiple agents. So solve this part first, and once you solve it, let each agent fill in the details on its own. Because once you have this global skeleton, I know what actions I'm in charge of in this global skeleton. What do I need to take care of? I have to now take into account the local aspects. Okay? Now remember, I didn't stress it enough, but the global actions can have also local preconditions. So the action of unloading a package at a location. Okay? Loading a package at a location is a global action because assuming multiple vehicles can reach this location. But for a truck to load a package in a certain location, it has to be in that location. And it being in that location is a private, is a local precondition of the action. So initially in the global coordination, we ignore all of these aspects, and now the agent has to fill in the details. I'll soon give you an example. Okay? And the thing is that the nice thing about this is we solve a much smaller planning problem, and now to fill in the details, each agent can do it on its own, completely separately, nothing, no interaction. But there's a potential for yes.
I have a question. What do you do if goal is a local variable?
If
a goal variable is local, how do you solve the global problem then if you don't have goal?
So I'm actually going to ignore this case. It's much easier to think of a situation where the goal is global. But if the goal is local, you can do the following things. So there's a simple trick you can do that will always work. Add a new goal variable, goal achieved. Okay. Have an action whose preconditions are basically basically all the original goal conditions. Okay? They could be global and local. Okay? That action, well, you know, this doesn't always work, but this is the gist of and then add this action to the relevant agent. If the goal is local to you, then it's your action of achieving the goal. And in order to achieve the goal, you're going to need that local fact to be true. Okay? So there's a way to go around this. But I suggest that for now we ignore this issue. It's solvable. Easiest thing to think about is that all the goals are global. But it's a very good point, yes.
Actually, related to this question, so this issue comes because of the definition of local and global. I mean, it looks like it could make sense that if a global precondition of a local variable affected by an action, so in some sense the effect should be global as well. So the definition that you have is not closed under causality.
Again.
So if an action can affect the local variable and involve have global preconditions, right? That's possible.
Yes.
It's not too reasonable that you have something global for an effect that's only going to be for the agent. Shouldn't that case global mapping to global?
If any action that mentions a single global variable, either in its precondition or in its effect, is a global action. The strict thing is that a fact is local if only a single agent can affect it, and an action is local only if all of its description, all the propositions that appear in its description are local to that agent. As long as there is one non-local fact in the description of an action, it's global.
Good. Then why this algorithm? Like you don't work with the global actions. So rather than throwing away local variables, why you don't throw away the local actions?
I throw the local what?
You have thrown away the local variables here.
No? Right, and the local action. Both of them. I'm throwing away I want to concentrate on basically the global facts. The global facts are not influenced by local facts. That's why I throw away the local action. Now, if privacy is not an issue, I could leave the local variables in the global action. Yes, you're right. Yes. The original term is not global and local. I added them in order not to get privacy into the matter, and it seems it's creeping in because I'm just too used to it. Global is called public originally, and local is called private. And I still have this in mind, although I tried to represent it completely independent. I agree with you. If we're not concerned with privacy, then I would leave the local variables for the global action. Okay, thanks. Okay, so this is a nice scheme. One thing that can happen though is that no one guarantees to us that a solution to this projected problem, so we projected out the local actions, no one guarantees that a solution to this problem is extendable by all, we have to feel that each agent has to make sure that it can actually deliver the global action in the solution plan. and for that it has to solve its own local planning problem, and maybe that's not solvable. So the fact that we found a global coordination plan doesn't mean that we can extend it necessarily to a complete plan, but if there is a solution, there will be a global skeleton that is extendable, but we may need to backtrack until we find it. Okay, so here's an example. Now it's clear. So we're going to try to switch packages between Beersheba, where I come from, and London. Okay? We have a package in Beersheba originally. We have a package in London, so in King's College. So we need to move it from my university to King's College, and we also need to move the package from King's College to my university. And we have a truck operating in Israel, a truck operating in London, and a plane that can fly between Tel Aviv Airport and Heathrow. So, this is a global skeleton plan. It mentions only global action. So the plane, and it's easier to think of it when you ignore the local variables, okay? So, the plane, okay, let's start with the Israeli traffic. We load the package. So notice that over here in the plan I also have these numbers, which are abstract time points, right? We need to say which action comes when. Since I'm not showing this as a sequential plan, I'm noting here that the time point in which it should be executed. So the Israeli truck reloads the package in Beersheba, and then it will unload it in the airport. Then at some point it reloads the other package in the airport, presumably that it's going to be there by then, and it's going to unload it in Beersheba. Similarly, the London truck is going to load the other package in King's College, then it's going to unload it in Heathrow, then it's going to load the package that arrives from Israel in Heathrow, and will unload it in King's College. And the plane, it will load the package that arrived from Beersheba in the airport in Tel Aviv. It will unload it later on in Heathrow. Then it will load the package that came from King's College at Heathrow and unload it in Tel Aviv. So basically, these are, all of these actions are global actions. And if you look at these actions and ask yourself, for each action, do we have its global preconditions in the plan? The answer is yes. For instance, for loading the package in Tel Aviv, the package has to be in Tel Aviv at an earlier time point, and this is taken care of by this unload action here. For unloading the package here, the package has to be in the plane, right? And this is ensured by this action. For, say, loading the package here, at Heathrow, package 1 at Heathrow, we have this action unload. We make sure that the package is at Heathrow. Okay? So, this is a global skeleton plan. It doesn't look at, it ignores completely the issue of the local aspects of the problem, which in our problem, the local aspects are locations of the trucks in the plane. Right? But if we ignore this issue, then this is a solution. Okay? So this is what it said. Notice that the truck and the plane location miraculously changes in our head, but in the formal description of the problem, there is the location is not mentioned. It's not a precondition nor an effect, and so this is a legal solution of that global planning problem. And now, after we've done this, so we basically have these are the actions, the global actions that the plane is supposed to perform. These are the global actions that the Israeli truck, these are the global actions of the London truck. And now they need to make sure that this is executable in the real world. And for this to be executable in the real world, they have to take care of the local precondition of all these actions. So initially, the plane is in Tel Aviv, that's not a problem. But then it's going to unload in Heathrow. How does this happen? Because we introduced this flight from Tel Aviv to Heathrow action. Similarly, it reloads the package in Heathrow, and then miraculously it was in Tel Aviv. In the global scenario, we fill in the information by making sure it flies. And similarly for the truck, moving from Beersheba to Tel Aviv, moving back from Tel Aviv to Beersheba, moving from King's College to Heathrow, moving back from Heathrow to King's College. Okay? Questions? Is the example clear? Okay? So this is a very simple algorithm. Ignore the local facts, solve the problem. The resulting thing is a sequence of action for each of the agents, and just make sure now to fill in the blank, fill in the detail, the local detail, so that it will work out. And if it doesn't work out, you need to seek a new global.
Sorry,
yes.
The numbers are the time steps, right?
Right.
And do they consider the global actions against locals as well?
Yeah, okay, so this is confusing when you look at, right? These numbers are not really time steps. They're basically giving us ordering constraints on the sequence of the order by which action should be executed. Okay, originally you can think of them as time points, but these are abstract time points because later on we're going to have to fill in the local facts. This is actually a problem where most of the actions are global, but there are many interesting scenarios, especially ones where this idea works very well, where many of the actions are actually local. So in order to move from one global action to the next global action, you can introduce many local actions in between. So what you need eventually is to generate a plan that respects the ordering of the global actions and make sure that the local actions appear in between. So this is not really going to be times 3 and times 4, but clearly there's something in between here. Okay? Is this point clear? So this is an important point to bear in mind. Okay. So, we're going to try to analyze this. And we want to know if this gives us any computational advantage. How does the decomposition show the effect of computation? And can we quantify the effect of the decomposition? This requires making the algorithm a little more precise. And I'm going to help Chris. For that, we're going to define the problem as a constraint satisfaction problem. Why? Because we have some understanding of the complexity of constraint satisfaction problems, and this will help us get some idea of the complexity of this approach. So, if you don't know what a constraint satisfaction problem is, I'm going to explain it briefly in this slide. It involves a set of variables with possible values, the domains of the variables. So in my example, we have x, y, and z, and the domain being 0 to 9. A set of constraints which are restrictions on the values that we allow these variables to have. For instance, x has to be greater than y and z has to be greater than x. And a solution is an assignment of a value to all of the variables such that the constraints are specified. So we have to assign a value from the legal domain to each of the variables, and the constraint has to be satisfied. For instance, x equals 5, y equals 2, z equals 7 satisfies these constraints. When we have a constraint satisfaction problem, it's important to define the constraint graph, which is a graph that has as its nodes the variables, and there's an edge between variables that appear in the same constraint. So you see here, x and y appear in the same constraint, so there's an edge between them. Z and x appear in the same constraint, so there's an edge between them. And what we know is that the complexity of finding a solution to a constraint satisfaction problem is in the order that is polynomial in how many variables we have in the problem, what is the size of the domain, and exponential is something that's called the tree width of this graph. How many people know the notion of tree width? Okay, I'll go over it. It's a very important notion in computer science, and especially in graph theory. Okay, but we'll get to it soon. So we can model the multi-agent planning problem as a constraint satisfaction problem. The variables will be one per agent, and it will represent its plan. Okay, so what are the values that each variable can get? The values are sequences of global actions of the agent. So, as in the example you've seen, each action has an abstract timestamp, like in this example, okay? And we constrain the number of actions to be bounded by some constant k. So this is a global plan for the agent that has 4 global actions. Okay, so we're going to allow as values for our variables sequences of actions that are bounded by this number. And so the size of the domain is exponential in the number of actions that we allow, right? We allow sequences of length k, so there's an exponential number of sequences of length k. Okay? So you have an option of either seeing me and going to see the Queen's parade. The helicopters are because of that I assume. Okay. Now, we define the variables, we define their values, now we have to say what are the constraints. So what are the constraints? So if we have this in your sequence, this says that action A is going to be performed at abstract time point t. And P is a precondition of action A. We have to make sure that someone supplies this precondition. So if you're familiar with partial order planning, these are the same ideas. Okay, I hope everyone here knows partial order planning, but so I have to make sure that P is satisfied when this action is executed. So some other pair, maybe belonging to the same agent but maybe to another agent, has to make sure that P is supplied, that it has to have the effect P at some time point that is earlier than T. And we have to make sure that no other action that occurs in between them will destroy P. That I will make sure that P will be true when we try to apply this action. So these are the global constraints. And the local constraints, there are only constraints on the sequences themselves. They're called unary constraints because they do not involve the action of the other agent. The local constraint is that we allow only global action sequences such that we can add local action in between the global actions that achieve their local preconditions. So basically, if we have here, so this is a solution. So you can see that these are the different agents, and here's a length 4 plan for each one of them. And if we can, this is a legal sequence only if you can fill in the details like we did here, so that this will actually be, they will actually be able to execute they will actually be able, okay, let's say it this way, that the local preconditions will also be satisfied when they reach these actions, okay? So the unary constraints are only with respect to their local variable, and the non-unary constraints, the global constraints have to do with the interaction between all of the global actions here. Maybe this action is supplying something for this action and so forth. Okay, so if we look at, I'm going to cheat here a little bit, and I don't have time to explain why I'm cheating and what's the solution. So if you caught me in a small lie, I'm happy to explain things offline. So the constraint graph for the problem is this one, right? Because the Israeli track only influences the plane, and the plane only, the London track only influences the plane, and the London track influences, the plane influences both of them, okay? So again, if you know a little bit about CSPs, I'm cheating, but in order to solve the problem, I'm going to have to spend a little more time than I want to, so be with me, take this as the whole truth. Okay, now in the case of multi-agent planning, we have this notion that is called the agent interaction graph, which turns out to be exactly the same as the constraint graph for our formulation. The agent interaction graph is basically says the nodes are the different agents, so we have 3 different agents, and we have an edge between the 2 nodes if there is an action, if there is a proposition that appears in the description of action of both of these agents. So for instance, the location of the package being at the Tel Aviv airport appears in the description of unload action for this, the load and unload action in the airport of the truck, and also the plane. But it doesn't appear in the London truck. The London truck cannot load or unload in the Tel Aviv airport. Similarly, the plane and the London truck also have shared prepositions that are affected by both of them. The package is being in Heathrow airport. If you look at the more, say, involved problem, where you also have another plane that can fly between different locations in the UK and trucks that serve these respective locations, then this is an agent interaction graph that you would get. Okay, the plane can only reach these airports, can only, doesn't interact with the user truck because it cannot reach Tel Aviv airport, but can reach all the airports in the UK. And the international plane only reaches Heathrow and Tel Aviv, so it can only interact with these three agents, and so forth.
Sorry,
Yeah.
Can I ask a short question? So here you're omitting the unary constraints, right, in this depiction. And the unary constraints, if I understand correctly, they act as sort of domain constraints, and they filter out, they basically make it so that only valid local plans exist in the domains of these
And we only accept the local plans for which there is a valid local extension.
in which there's a valid local extension. So basically, you are doing the local, or you're encoding the local planning as these unary constraints.
Exactly, yes.
Okay.
Okay.
Thanks.
It's an important point, but I'll mention it briefly. But again, I'm cheating here and there for the sake of simplicity. Okay, so ignoring local planning. Okay, that's checking the unary constraints. Exactly what you mentioned. We're left with solving the global CSP, and we're going to ignore local planning and we assume it's easy. Okay. So the complexity of solving the CSP is exponential in the tree width of its constraint graph, so which is exactly this agent interaction graph. So I'll explain this idea of tree width soon, but basically the complexity of solving the planning problem is exponential in the width of the respective graph and in the size of the domains of the different variables. Okay? So let's see what's this idea of tree width is. If you don't know it, it's a very useful notion to know. So we'll step back a little bit. So you know that graph algorithms are often much easier when the graph is a tree. Many graph algorithms are linear time or lower polynomial if the graph is a tree. But what happens when we want to work with something which is not a tree? Then one way to do this is to generate a tree. And that's called the join tree of the graph. So you have this graph, it's not a tree. We can generate a tree, but the tree nodes are sets of nodes of the original graph. Okay, so you see here, the node here contains A, B, and C. So it's a subset of the nodes in this graph. Okay. So a join tree is a tree whose nodes are subsets of the sets of the original graph that satisfies two properties. One property, every click that exists in the original graph has to be within one of the nodes in the join tree. So for instance, you see this click ABC, it's here. You see this click EGH, it's here. You see this click EB, it's here. It's also here. Okay? And the other property is called the running intersection property. This basically says that if you have a node if you have an original graph node in one of the tree nodes, in any two tree nodes, say this A is not even B, okay, B here and B here. It has to appear in all the nodes on the path between these two nodes. So in the tree we only have a simple path between every two nodes. So if you have B here and B here, it has to be all the way through. You can see this, C here and C here and all the way through. E here and E here, all the way through. Okay? So this is a join tree. And then you can basically run a tree algorithm on this graph, where basically the variable that you have here is a Cartesian product of the original variables. So the tree width, the width of this join tree is 1 minus the largest subset in the tree. So in this particular example, all subsets are of size 3. So the largest one is of course size 3. So this has a width of 2. And the tree width of a graph is the minimal width of any of its join trees. So assuming this is the smallest this is the best we can do for this graph, then the tree width of this graph is also 2. 1 minus the side of the largest node. So why do we care about this? Okay, before that, let's look at the example. So here's a graph, okay? And here's a geometry for this graph, okay? And the width is 1, because the largest subset is 2, minus 1 is 1. Here's the other graph. Here's the geometry for this graph. You see the largest node is this one, which has 3 variables in it. So the width of this graph is 2. Okay, so I hope you understand this concept of tree width. So now we can analyze the complexity of the algorithm that I've shown you. And the complexity is derived from the fact that we model this constraint satisfaction problem. It's exponential in the constraint graph's width and polynomial in the size of the domain. Okay, so the constraint graph's width is basically the width of this agent interaction graph. And if our planning problem, multi-agent planning problem, is loosely coupled, we expect this to be something that is small. Okay? Something that is small. So if the tree width is constant or maybe logarithmic in the number of agents, then this would be a loosely coupled problem. And again, if we assume that our agents interact only, each agent interacts only with a small number of other agents, then this makes sense. The domain size for a problem is the number of, remember the variables for us were represented sequences of actions. So how many sequences of actions exist? Well, it's the number is exponential in this bound on the left of the sequence, which we call the k. So suppose we think of the algorithm as follows. We run the following algorithm. We gradually increase k and solve the constraint satisfaction problem. So we bound the length of the sequences, say, to be 5. Okay? Then we solve the constraint satisfaction problem that corresponds to the multi-agent planning problem for this case. We don't find a solution, then we increase k. Now we move to 6. We don't find a solution, we increase k, we move to 7. So when are we going to stop? We're going to stop at when k equals what we'll call delta, which is the minimum over the maximum global agent action in the plan. So if you look at a certain plan for this multi-agent planning problem, look at the agent that does most of the work. If we gradually increase the size of the sequences, when are we going to stop? When we find the plan for which the agent that works hardest has the smallest number of actions. Because we're gradually increasing the bound on the length of the action that each agent does. Okay? This bound has to be at least as big as a number of actions that the agent that does most of the work will do for us to find this plan. When will this happen? When this bound is indeed the value of the number of actions done by the agent that works the hardest, and when we're looking at the plan where the agent that works the hardest does the least work relative to other plans. Okay? So, the bottom line of all of this is that if you have a loosely coupled planning problem, say the tree width of the agent interaction graph is either constant or logarithmic, and the number of global actions, remember this is global action, the set of actions of the agent performs consists of the global action and the local action. But if the number of global actions that the agent performs is not too large, say constant or logarithmic, then you have a polynomial time algorithm that solves multi-agent planning. And that's interesting. You had a lecture on complexity of planning. I don't know if you mentioned this, but this is an interesting result for single-agent planning. It shows you when planning by decomposition allows you to solve planning problems in polynomial time. Okay? So, what do you suggest that we the next thing is, I have just do this. Okay.
Question.
Yeah.
May I?
Yeah, sure.
So, when you just described here, I mean, it's interesting. It's a bit reminiscent of cut-set conditioning, and I would think that that kind of technique would apply when you have a loosely coupled problem, because you can just, because it's very close to a tree already, probably, you can just factor out a node and then try with all domain values.
But the complexity is similar, right?
Yeah.
I mean, by the way, it's interesting. It would be interesting to see a clear formulation of this using cut-set conditioning instead of what I described here. I haven't seen anyone explicitly talk about it.
Okay, that's interesting. One thing though that I'm not still sure I completely understand. Still, your domain size is exponential, right? In K is bounded, but
so that's why I require K to be small.
Yeah, right.
If it's constant or logarithmic in the number of agents, then this would still be polynomial, right?
Sure. Yeah.
And again, this makes sense. On the face of it, it wouldn't make sense if I required each agent to execute a bounded number of actions or a logarithmic number of actions only. But these are only global actions. So if you have a domain in which the coordination part, the point is that this alludes to the coordination part of the plan. So if the coordination part of the plan we don't need to coordinate so much. I need to perform actions that coordinate with you, but not too many, okay? But I may have a lot of work to do on my own to set up things, okay? But then this will be polynomial. I'll show this soon in experimental results.
Interesting.
Okay. So, this algorithm that I mentioned now is completely centralized. We're solving a centralized CSP, but it's easy to distribute. Why? Well, at least in theory, okay? CSPs there's a whole community that works on distributed CSP algorithms. Take any of the distributed CSP algorithms and use it to solve the problem. You have a distributed algorithm for solving planning problems. In practice, doing it in this way is not going to work because distributed CSP algorithms make a lot of strong assumptions. First of all, they assume only binary constraints. That means that in our case, it means that only groups of two agents will have shared proposition. And they also have very weak heuristics for, let's say this way. The heuristics are very weak for this domain. They don't have special heuristics, maybe Chris will correct me, but they don't have special heuristics that are useful for these domains. So what you can actually take this idea, introduce some ideas from planning and planning heuristics, and make this into a reasonable approach. So in the original work on this, you can see here some results. What I want to illustrate here are two things. First of all, even originally when this was first tried with very weak heuristics and with additional requirements of privacy and so forth, there were cases where using this idea we were able to solve problems that you couldn't solve with a regular single agent planning problem. These two domains, rover and satellite, are very loosely coupled. Very loosely coupled. Logistics is not as loosely coupled as it. And this is why it was easier for this planner to solve problems than for FF. And what you see here in the parentheses is the size of delta. This is a maximal number of global action performed by any of the agents. You see, very, very small number. And once you move beyond that, once you increase the number of global actions that each agent has to perform, basically it's, crashes. Okay? Now this is not the state of the art, but this is just illustrating the 2 points that I wanted to mention. First of all, the fact that if it's very loosely coupled, if it's loosely coupled and the number of coordinating actions is small, then this can be very efficient. So, is this idea useful? So coming up with a decomposition is not always easy. I'm going to briefly talk about some work on doing it automatically, but again, this is not expected to work everywhere. Not every problem is suitable for decomposition. And the original CSP method hits the wall pretty quickly, as you've seen, but the idea of decomposing into global coordination followed by local planning is very useful. If you do not insist on a complete algorithm with a clear theoretical bounds, and you just look at something practical, you can actually get very powerful algorithm in practice. Okay, it's also provided some new characterization of planning problems with polynomial time solution. So we should take a break now.
The issues that the breakfast.
The
There's special instruction for the coffee break today.
Sorry?
There's special instructions for today's coffee break.
Oh.
So maybe we can have a break now.
Oh, we could take a break now.
Yeah.
If this is a good moment.
This is a good point, so we'll take a